Hi everyone, welcome to the third lecture of this 7th week of this course on microsensors and nanosensors. We were discussing about force sensors. In today's class, we are going to discuss two different kind of force sensors that are based on piezoresistive phenomena as well as piezoelectric phenomena. Okay, so let's discuss piezoresistive force sensors first, and then we will take the piezoelectric force sensors. Piezoresistive force sensors are actually the most common force sensors that exist. In fact, piezoelectric force mechanism is the most common methodology on which micro force sensors can be based upon, or it's inherent to a piezoresistive material to measure the force applied. Okay. Basically, these piezoresistive materials offer a direct conversion of mechanical deformation into electrical currents, okay, or some other parameter that we will see. Not exactly current, but say in the form of change in resistance or some other form. Okay. As I have mentioned that these sensors are basically piezo resistive force sensors. So as the name suggests, they are based on piezo-resistive effect. Okay, piezo-resistive effect we have already discussed in our previous modules. Okay, particularly in the module 2 where we discussed about different effects. However, I will just recall it for you. What happened that when a metal or a semiconductor material is subjected to some external stress, its resistance changes in proportional to the deformation that happened in the material. Okay, so when you have a say material, this material can be a metal or a semiconductor that we'll see in a while. Okay, when you apply a force, okay, or say stress, okay, there is some deformation happening in the material. It depends on what kind of force you are applying, okay, and accordingly this material changes its resistance if it is a piezo resistive material. Okay, and that's why I mentioned initially that this is the inherent characteristic of a piezo resistive material to tell about the applied force. Okay, please note that this piezo resistive materials or piezoresistive effect is different than the piezoelectric effect. Okay, if you can recall, the piezoelectric effect generates a charge or a voltage, right? If you remember, we utilized charge amplifiers, or when we discuss this piezoelectric effect, we have also talked about charge amplifiers, which is required to amplify the signal which is coming out of this piezoelectric sensors, right? However, piezo-resistive devices are different, okay, where you have change in the form of resistance. Okay, so piezoresistivity is all about change in resistance. I am telling again and again because the principle of operation of piezoresistive force sensors and piezoelectric force sensors are quite different, and in today's lecture we are going to cover both of them, okay, so that it becomes very easy for you to differentiate or segregate between two different devices. Okay, so in the piezoresistive material, what I am telling that when you are applying some force, or if you are applying some stress, there is a deformation and subsequently there is a change in the resistance of the material. Okay, so when you are applying a stress, what you are doing actually, you are deforming the material's crystal lattice. Okay, and this deformation alters the mobility and concentration of charge carriers. So if it is a metal, you are actually disrupting the charge movement of the electron, while if it is a n-type or p-type semiconductor, you are actually changing the mobility and the concentration of the electron as well as holes. Okay, and that's how it reflects as a change in electrical resistance. Okay, so that is how a piezoresistive piezoresistive material work. You already know that, but I just recalled it for this discussion. Okay, So, as we are discussing the piezoresistive force sensor, the working principle is very simple, as any piezoresistive device works. So, you apply the force, you have a variation in resistance in the piezoresistive material, and you measure that force, okay, that has been applied to the material. Okay. So, mostly these materials include the semiconductors like silicon, germanium. Okay. However, some metals also shows piezoresistive effect, including iron and copper. Some metal oxides also have these piezoresistive properties. Okay. And then we have polymers. Quite a few polymers also shows these piezoresistive properties. So, you have polyline in the form of pani, or polypyrrole PPY. They are very good piezoresistive material. Okay. And polysilicon, which you already know is very popular gate material in transistors. Okay. It also shows some piezoresistive materials. Okay. So, that is why piezoresistive property. So, there is a separate class of sensor based on force sensor based on polysilicon based material. And okay, and the basic structure of a piezoresistive force sensor is something like this. You have electrodes, okay, and you have the piezoresistive material, depending on what kind of your device is on the surface or a complete substrate as a piezoresistive material, and then you have a force, and these metal electrodes capture this change in resistance, okay, with the applied force. Okay. The basic formula to calculate or to establish the change in resistance with the deformation is a simple strain factor or gauge factor relationship, where you have delta R by R equal to gauge factor into del L by L, where delta RS is the resistance variation of this strain gauge or resistance variation of this piezoresistive material, okay, due to deformation, and RS is the resistance of the initial resistance of the piezoresistive material or the strain gauge, which is based on this piezoresistive principle. Okay. And GF is the strain factor or gauge factor, okay, which is a dimensionless quantity. Delta L is the length variation of the strain gauge due to deformation, while L is the length of the strain gauge when there was no deformation. Okay. So, using this equation of a simple strain gauge, okay, you can also calculate the variation in the piezoresistive materials. Okay. The basic structure of a piezoresistive force sensor looks like this. You have a silicon substrate, sometimes it can be glass also, okay, and you have this area where you applied the force, and this piezo resistors, which is micro machined on the surface, they measure the applied force, or they changes their resistances. This is piezo resistor PR1 and this is PR2. Okay. So, they changes their respective resistances when there is a applied force. Okay. However, this is just a schematic, it can be of various type. Okay. So, there are basically three different type of piezoresistive force sensor depending on what material it is using and how they are fabricated. Okay. So, you have bulk silicon piezoresistive force sensors, you have MEMS based piezoresistive force sensors, again based on silicon only, but different form of silicon. Okay. And then you have flexible polymer based piezoresistive force sensors. You can have other kind of piezoresistive force sensors also, like based on metal oxides, but their market presence is not very high. Okay. So, this is the basic types of or categories of piezoresistive force sensors that are used throughout the industry. Okay. So, let us quickly see what is a bulk silicon piezoresistive force sensor, and then we will also quickly see this MEMS based piezoresistive force sensor and flexible polymer based piezoresistive force sensors. Okay. So, let us quickly see what is a bulk silicon piezoresistive force sensors. Okay. The basic structure of a piezoresistive silicon based or bulk silicon based piezoresistive force sensors is something like this. you have bulk silicon on which directly you are applying the force. Okay. Then you have this piezoresistor. I will talk about this piezoresistor in a while. Okay. And then you have a metal contact. Okay. So these bulk silicon piezoresistive force sensors are a type of force sensor that exploit the piezoresistive effect of silicon directly. Okay. So you are not using any other things. So what you are doing is you are harnessing the piezoresistive property of bulk silicon directly. Okay. So bulk silicon sensor or bulk silicon piezoresistive force sensor uses the substrate itself as a sensing material, as you can see in this figure. Okay. So usually what happens is you use a very high purity single crystal silicon as a substrate in this case. Okay. And I mean, this is, I am talking about in the form of some platelets, but it also exists in the form of diaphragm. It can also exist in the form of cantilever. It can also exist in the form of beams. Okay, it depends what configuration you are giving. Okay, but all of these structures can be deformed by some external force. Okay. Now let's talk about this piezoresistive element in this bulk silicon. Okay. So this is basically the diffused or the doped region aligned in a specific crystallographic direction for maximum sensitivity. What we actually do is we dope this some part of this bulk silicon, okay, which acts as a point for this piezoresistive material. Okay. And what you do is you take this metal contacts from here. Usually this kind of device is mostly connected in a form of Wheatstone bridge. Okay. So if you talk about a bridge configuration, this sensor can be present in a arm of this Wheatstone bridge. We call it a sensing arm. Okay. So usually it is attached to this bridge through this metal contact. Okay. The application of this bulk silicon piezoresistive force sensors are tremendous. Okay. They are very popular for the load cells. In the blood pressure transducers also, a little bulky type, they were used. Okay. Then in the gaming devices, they are very popular. Okay. In the tire pressure sensors also, earlier it was used, but nowadays they are being replaced with the MEMS kind of devices, which is our next topic. Okay. And in the airbag systems of a vehicle, okay, they are very popular. Okay. However, there are certain limitations of this bulk silicon based piezoresistive force sensor. Some of the limitations that this devices has is they require temperature compensation to maintain accuracy. So they are susceptible to the change in the ambient, particularly the temperature. Okay. Then they have limited use because of their mechanical demanding environment, because silicon is brittle, so you cannot apply any amount of force that you want on this silicon diaphragm, or be it cantilever or whatever structure. Okay. So at higher force, the relationship between force and resistance can become nonlinear. So basically, to certain Newton force applied or certain micronewton force applied, the devices are linear, but after that it becomes non-linear. So you have to be very specific that in which region these sensors are being operated. Okay. The creep of these devices can affect the long-term measurements. So you have to be very, very particular about the slow change in the output under the constant load of this kind of sensors. Okay. They are not suitable for very high force applications without any external mechanical damping or protection. So you should always provide some damping or external protection to this kind of force sensors. Okay. Then important thing is the packaging of these devices are very, very unique. So it should be carefully packaged to isolate it from the ambient, to safeguard it under the mechanical stress. Okay. The output of this kind of device is usually very low. Okay. So you need some extra amplifier units to amplify the signal out of this bulk silicon based piezoresistive force sensors. So basically what is needed is a new generation of piezoresistive force sensors. It can be based on silicon itself, okay. And with the rise in MEMS technology, MEMS based piezoresistive force sensors has evolved, okay, since 1980s or so, okay. The basic structure of a basic layout of a MEMS based piezoresistive force sensors is something like this. You have a piezoresistive polysilicon over here, okay, on top of which you have metal interconnect layers, okay. Then you have multiple suspended structures and sacrificial layers, okay. So you have this suspended membrane and the sacrificial layer, which can be removed by micromachining, okay, or by etching, okay. So this kind of MEMS based piezoresistive force sensors are usually fabricated on top surface of silicon wafer by surface micromachining, okay. Their structure layer is mostly of polysilicon, as we have just discussed. This piezoresistive material used in this kind of MEMS piezoresistive force sensors are basically polysilicon, okay. I mean, lot of fabrication steps are involved in fabricating this kind of device, okay. And since you have seen that there are suspended membranes and you have sacrificial layers, so multiple level of deposition steps and multiple steps of removal, which is we call it in fabrication as etching, is required for this kind, for fabrication of MEMS based piezoresistive force sensors, okay. However, the advantage of this MEMS based piezoresistive force sensors are they can be miniaturized as a small electronic chip of size say 1 mm or even smaller, okay. And although it goes through a clean room and other protocols, you have to spend a lot if you want to fabricate a single MEMS based piezoresistive force sensor. But when you talk about batch fabrication, this is quite possible, because usually if you talk about even in a lab, we process at least 4-inch or 6-inch wafer on which hundreds of devices can be mounted, okay. If you talk about industry which rely upon 300 mm wafer, okay, thousands of such devices can be fabricated in one go, okay. So batch fabrication is possible, which bring the cost much lower as compared to the individual device fabrication techniques, okay. And the sensitivity of these devices are very high, okay. So that's why they are very popular in the personalized devices or say household devices, okay. Then the sensitivity of this MEMS kind of devices are also very high, okay. And it can be integrated with the existing technology. It can be integrated with the electronic system that exists. So they are very popular in case of miniaturized electronic devices, okay. However, the challenge of this MEMS based piezoresistive force sensors are first I have already mentioned is about fabrication, okay. So you face lot of challenges when you fabricate such device in a clean room, okay. Then temperature sensitivity is another point that we should not forget. These devices still suffer from drift in the changing ambient, okay. Then mechanical reliability of this system is also questionable. However, you can protect it by selective packaging techniques, but then packaging itself become very complicated, so which is also a kind of limitation in this kind of devices, okay. Also, the output of these devices are not very high, okay. So the signal noise is inherent to this kind of devices, okay. Now, next kind of piezoresistive force sensors are flexible polymer based piezoresistive force sensor, okay, and this has become very popular nowadays, particularly with the rise of this wearable devices, okay. So mostly the structure of a flexible polymer based piezoresistive force sensor is something like this. You have a polymer substrate, you have a conducting layer, and then you have a piezoresistive element which is also a kind of polymer, okay, and then you have a flexible polymer on the top. You have different electrodes and then you apply a force. Okay, so the conductive layer is mostly composites of stretchable polymer like PDMS and carbon nanotubes. Okay, and the substrates are again PDMS or Ecoflex kind of material. Okay, there are various fabrication strategies, but mostly you cannot use conventional lithography techniques, be it electron beam lithography or be it photolithography. Okay, so it can be fabricated by different printing techniques like screen printing, inkjet printing, aerosol jet printing, that kind of devices, that kind of techniques. Okay, nowadays 3D printing is on rise for microelectronics and nanoelectronics, and 3D printing can also be used for printing this kind of devices. Okay, but at laboratory scale you can also use a simple spin coating to fabricate different layers of this polymer substrate, conductive layer, then a piezoresistive layer, and then flexible polymer. So it can also be subsequently spin coated on a polymer substrate. Okay, so this kind of devices along with the printing techniques can also be made in a laboratory at a laboratory scale using a spin coating tool. Okay, the advantage of this polymer based piezoresistive force sensors are they are lightweight and flexible, and that's why they find their application in wearable devices. Okay, the cost of these devices are also not very high because the substrate on which they are fabricated are cost effective, as well as the process that they are using, it can be roll to roll fabrication also. So the cost associated with the fabrication of this flexible polymer based piezoresistive force sensors are also not very high. Okay, then another advantage of this flexible polymer based piezoresistive force sensors are they can be customized in different form factors as well as on different substrates. Okay, so that is the biggest advantage that is associated with the flexible polymer based piezoresistive force sensors. However, there are different challenges in terms of long term durability of these devices, particularly these polymers degrades over the time. Okay, and that is of the biggest concern for fabricating this kind of devices. Okay, then environmental stability of these devices are also questionable, and they have variations with ambient conditions like with changing humidity condition or with changing in the temperature conditions. Okay, for that kind of challenges, what you do is you have various other sacrificial layers that are coated on these devices, but then that is beyond the scope of discussion of this class. Okay, then another challenge of these devices are the fabrication reproducibility. Okay, since you are using various printing techniques or even you are using a spin coating technique, okay, you cannot have precision that you had in the lithography system. Okay, there, say for example, in say MEMS based devices, you have already made a mask where you have patterned electrode. Say I have a mask where I have patterned these electrodes of having openings, or you can expect that when it is transferred to the device, these openings are say 800 nanometer. Okay, this is 800 nanometer or say 1 micron, right? Now, if you talk about the flexible polymer based piezoresistive devices, okay, you are making the contacts also using spin coating, for example. Okay, now initially in the first go you had a so you drop casted this, say AG ink, for example. Okay, or say even PDMS on top. Okay, and you expected a dia of around 1 micron. Okay, in the next go, if you do, okay, this can be 1.1 micron. In the next go, you can expect 1.15 micron. Controlling exact dimension as you have control in this lithography techniques is not possible in case of flexible polymer based piezoresistive force sensors. But then there are some advanced printers coming into the market which can pitch the accuracy as achievable in the lithography techniques. Okay, they are very, very precise and can lead to very accurate devices with very less device to device variations. Okay, so this is all about the piezoresistive force sensors. Let us also see quickly the piezoelectric force sensors, because they are also very, very important, particularly while measuring the dynamic forces. Okay, so these piezoelectric devices are very, very important when you talk about measurement of dynamic forces, and that's why when we will discuss the accelerometers, there we will see that most of the accelerometers are based on this piezoelectric behavior. Okay, so this piezoelectric force sensors can be extended to be used as a piezoelectric accelerometers. Okay, as you know that force and acceleration are related through mass. Okay, so they can be extended to the accelerometers. Okay, so let us quickly learn about piezoelectric force sensors. So piezoelectric effect, as I have already mentioned, can is nothing but when you have a piezoelectric material, when you apply certain force, okay, there is a change in the charge or there is a change in the voltage, or when you apply some stress or applied some force, the deformation can be visible in the form of charge or in the form of some voltage. Okay, and that happens because of polarization of charges. We have covered this piezoelectric effect in detail in the previous models. Okay, you can go ahead and see those lectures. Okay, piezoelectric effect can be used for both active and passive force sensors. So either you are making a passive force sensor or you are making a active force sensor, you can still use the piezoelectric effect. Okay, so as I have mentioned that it is based on the piezoelectric effect, where the changing force is converted into some electrical signal. Okay, while the electrical response is 0 for steady state force, when an active excitation signal is supplied to the sensor, applied force can change some property of the material that would affect the piezoelectric response. Okay, so basically the output is in the form of either change in the charge or change in the voltage. Okay, mostly we have seen that there are natural piezoelectric materials and there are artificial piezoelectric materials. Okay, natural piezoelectric material, the best example of natural piezoelectric material is a quartz crystal, and example of a artificial piezoelectric material is a, say, PVDF. Okay, so let's talk about natural quartz crystal. Okay, so the basic idea behind this sensor's operation is the change in the resonant frequency. Okay, of say existing quartz crystal. Okay, so certain cuts of the quartz crystal are used as a resonator in electronic oscillator. We know that. Okay, so it shifts resonant frequency when there is a mechanical load. When you have applied some load, okay, there is a change in the resonant frequency. Okay, so the natural mechanical frequency spectrum of a piezoelectric oscillator can be given by a simple equation as F equal to n by 2L under root C by rho, where this n represents the harmonic number. Okay, L is the resonance determining dimension. Okay, your C is the effective elastic stiffness constant, while rho is the density of the crystal material. Okay, so this is the natural frequency. Okay, the frequency shifts, this frequency shift generated by an external force is because of non-linear effect within the crystal. Okay, when you deform, we have already seen that there is a certain kind of polarization because of which there is a charge generated, or along with that there is a frequency shift. Okay, so in this equation the stiffness constant change, the C changes on application of the stress value. Okay, so when you are giving certain amount of force, there is a change in this C. Okay, the effect of stress is negligible on the strain as well as on the density. Okay, please note that minimal sensitivity to external force can be achieved when the compressed dimension is aligned along specific direction for a given crystal cut. Okay. These directions are typically considered during the design of crystal oscillators. Okay. When you design the crystal oscillator, you consider these directions very carefully. Okay. When their mechanical stability is very important, right? When you design this crystal oscillator, their mechanical stability is very crucial, and that's why you consider these directions there. Okay. But in this case, when we are talking about force sensor, we are not interested in minimal sensitivity. What we are trying here is the maximize the sensitivity. Okay. So basically the objective is just opposite. Here my objective is to maximize the sensitivity to force, okay, or to stress along with the specific axes which I already know. Okay. So based on what axis I am applying the force or the stress is being applied, you have different type of piezoelectric force sensor. You have compression sensors, you have shear force sensors, and you have bending piezoelectric force sensors, depending on what kind of stress you are applying, and based on that the measurement of force will be also be in that particular direction. Okay. The high performance pressure transducer, the diametric force is used. Okay. Why I am talking about this diametric force? Because we have just seen now that the direction of the applied force or the direction of the cut in this quartz crystals are very important. Okay. So the application of piezoelectric force sensors are mostly in the measurement of dynamic force sensor, but it doesn't mean that it cannot measure the static force. It can also be used for that. Okay. But majority of the piezoelectric force sensors are used for measuring the dynamic force events. Okay. You will find that in the micro robotic systems and machinery, these kind of piezoelectric force sensors are used. Okay. In the micro machines where there is a micro engines or there are small thrusters, okay, this are used as engine knock sensors. Okay. And in basically in the structural monitoring of a building, okay, or a huge structures, these piezoelectric force sensor arrays are used. Okay. These piezoelectric force sensors, based on their operations, they can also be categorized under load cells and impact hammers. Okay. The piezoelectric load cells detect and measure the force transmitted through the sensor when subjected to external stimuli, for example, a vibration or impact. Okay. While impact hammers are very important and can be used to apply an impact to a material and measure the actual amount of force applied. Okay. I hope the difference between the piezoelectric force sensor working as a load cell and piezoelectric force sensor when they are operated as a impact hammers are clear to you. Okay. Please note that the sensor manufacturers make load cells and impact hammers with varying sensitivity, and other parameters also are changed when they are making a impact hammer or a piezoelectric load cells. Okay. So I hope that the piezo resistive force sensors and piezoelectric force sensors are very clear to you. We will be using the concept of this piezoresistive force sensors and piezoelectric force sensors when we will discuss the pressure sensors, as well as when we will talk about tactile sensors. So if you understand these concepts, okay, it will be very easy for you to understand the concepts of pressure sensors, because we will be extending these sensors in the discussion of pressure sensors or micro pressure sensors. Okay. I hope that these things are clear. We will be discussing some other force sensors in our next lecture, which is the fourth lecture. Okay. So let us also understand some of the advantages of piezoelectric force sensors. The high sensitivity and fast response associated with these piezoelectric micro force sensors are very crucial, because mostly this piezoresistive force sensor that we have discussed a while ago may not be enough as compared to this piezoelectric force sensor. Their durability is very good as compared to other kind of force sensor, as well as you can have a rugged kind of device, rugged kind of piezoelectric force sensor. No external power is needed for sensing element. Okay, that is not the case in case of the piezoresistive or the capacitive force sensor. Okay, everywhere you have to use some external power. Okay, in this case you do not have to explicitly use a power supply. So of course for the interface circuit and others you may need to give some biasing and other things, but explicitly to run the device you do not need any external power. Okay, and the dynamic range of these devices are quite high. Okay, however, it is not that everything is good about this piezoelectric force sensor. It also have certain limitations, like it cannot measure the static forces as accurately as it can measure the dynamic forces. It can still measure the static forces, but the accuracy will not be as high as it was for dynamic forces. Okay, these piezoelectric force sensors will require high impedance charge sensors, charge amplifiers explicitly for their operation. Okay, since the signals are very small, okay, you need the high impedance charge amplifiers, which are not cost effective. Okay, still these sensors like the piezoresistive devices still suffer from temperature variations, and you may require external temperature compensation circuit for the operation of this piezoelectric force sensors also. Okay, so with this we are finishing this piezoelectric force sensors. We have also discussed today the piezoresistive kind of sensors, and I hope that the difference between piezoresistive force sensors and piezoelectric force sensors are clear to you. We will be using the concepts that we have discussed today either in the piezoresistive area or in the piezoelectric force sensor in the discussion of tactile sensors and pressure sensors, which are the topics in our next lectures. Okay, thank you.